choose where to start with. Yes. So I implemented it in 2014. So it's also current. At the time, it was really basic. We were using I will use it basic. So we have basic around. And we can also change this. It has to be portfolio. And people need it to be implemented, so it's implemented but to see the benefits that
Okay.
And so because this is so I'm not curious. So I can do this. Time to validate.
Okay, we wait another 1 minute or 2 minutes, and then we will start the meeting.
I brought them. Should be added to your
And the change that the thing is almost the thing is almost
I'll get to. Yeah, but I think I see.
Okay, shall we start? So welcome TCPM working group meeting. So please make sure you are in the right room for the meeting. And before we start, please aware the note well. I think you're already familiar with this one, but just in case, by participating IETF, that means you agree to follow IETF processes and policies. If you have any concerns about it, please read this note well very carefully. Basically, you can find the same contents on the IETF webpage. And logistics, thanks for Gori and Richard for note taking. And we might want to one person who takes kind of meter echo. And if you could volunteer for checking meter echo, that would be great. Thank you. And this is a simple reminder. When you speak up during the meeting, please say your name at mic before you speak up something so that a note taker can track your name in the minute. And also when you submit your individual internet draft, please include TCPM in your draft name so that chairs can track the status of your draft.
Just as Deborah described, I will be typing down the people's names as I read them off when they're standing here talking. So everybody make sure that I can read your badge while you're standing here.
Okay. And as we already announced, in this Bangkok meeting, we have two slots. The first slot, which we are having right now, has 4 items. First, the chair will talk about the working group status. And then after that, Carles will talk about TCP Constraint Node Networks draft. And this draft is actually a working group item or LWIG working group. However, this draft contains many TCP stuff. So it is to some extent TCPM related. So both LWIG working group chair and TCPM working group chair agreed to run working group Rust call on both working group once this draft becomes ready. And then according to the authors, this draft is getting ready for the working group Rust call. So that's why we're having discussion on this draft in this meeting so that we can check this draft is ready from the TCPM working group's point of view. That's why we allocated 20 minutes for this presentation. And the next item is generate ECN, and Bob talks about his draft. This is already working group item in this working group. And then after this, Bob will also talk about RAC plus L4S. And this L4S is, as you know, the working group item in TSPWG. But in this presentation, he will more focusing on implication of RACs and L4S. And that's the topic for slot 1. Any questions so far? And then we have second slot on Tuesday, tomorrow, from 11 to 12. And this is a special session to discuss congestion control and loss recovery mechanism in QUIC and TCP. And Jana and Ian will lead this session. And I will talk more about this one at the end of my slide. Any questions so far? Okay. So now I'll move on to the status of document. And so we have finished alternative backoff ECN draft a couple of months ago. And today, about 1 hour ago or something, we have received an email from the IESG that they have approved this draft. So this draft will be published very soon. And thank you so much for your cooperation. And then we have several working group documents and generalized ECN. This draft has been updated recently, and then this is one of the agenda items for today. And RTO consider draft, this draft just has been updated about a week ago, and I will talk about a little bit more after this. Also, 1793 base this is also updated recently, and so it's keep updating, keep progressing. And also TCPM converter draft has been updated recently, a week ago. So if you are interested, please read and please give us a feedback. And then accurate ECN, we don't have updates since July, but we are expecting that new version will come from the author, at least by the next IETF. And TCPM rack, this draft has not been updated since July, but I think, basically we are expecting some feedback, mainly from implementers. And so if you can have some opinions or feedbacks, and please let us know. And then so that author can update a new version. And EDO draft, there is no big update EDM draft for a while, but according to the author, they are doing some experiments. So once they have some result from the experiment, they will come back with new version. That's the status. So any question about the working group document? Okay. So now I will talk about RTO consider draft a little bit more. This draft has been suspended for some reason for a while, but now we got new version about 1 week ago. And one of the reasons for the suspended for a long time was we have very long discussion about how to sort out the requirement in this document and the other document, and such as RFC 6298 or RFC 8085 or 793 bis, etc. And so one tricky thing is, if one draft says this is must, and if the other draft says this should, what's the message we should, give the readers? That kind of thing has, results in very long discussion. And because of that, we have very long discussion, and after that, we suspended for a while. And then recently, we have very nice discussion with authors. And then authors basically update the draft to address these issues. So basically, the authors create a new section, which is section 2. And then in this section, they also describe what's the motivation of this draft, which kind of situation that this draft can be useful, and if there is some difference between the requirement of this draft and the other draft, how you should solve it, how you read this draft of the message. That's the point of the new updates. And so the chairs think this update is pretty nice, and then we are expecting this can solve the previous, very, long discussion. And so basically what we are, asking you guys is please read this draft and please give us feedback. And if this new section solves the, previous conflict. And then if people think this, new version looks very good, we can start thinking about, publishing a draft, initiating working group of this draft so that we can publish this draft. I think this draft is to some extent useful for some situations. So that's why we're thinking about this kind of thing. So any opinions? Any opinions? Well, if you already read this draft and you have opinion on it, now it's a good chance to speak up your opinion. Okay, move on to the next one. And then, as I mentioned, we will have a second slot for TCPM meeting. It's tomorrow, Tuesday, from 11:20 to 12:20. And this is a special session to discuss congestion control and loss recovery mechanism in Quick and TCP. And so, as you know, Quick utilizes lots of TCP's mechanism for loss recovery and congestion control. But since Quick and TCP is different protocol, the loss recovery and the congestion control mechanism is slightly different. And then So we would like to discuss why this is different and what's the implication of this difference. And then by doing this, we might be able to learn from Quick what we can contribute to Quick. In any case, I think this will be useful discussion for both Quick and TCPM working group. And since we have 1 hour, basically we started from key mechanism in Quick because we think some folks may not familiar with Quick's mechanism. So the Ian and Jana will talk about the basic Quick mechanism. And then after that, we dive into loss detection and congestion control mechanism with comparison to TCP. That's the plan. So, any question? Okay, so please attend tomorrow's session as well. We appreciate your cooperation. Okay, let's move on to the presentation. Karis?
Hello everyone, my name is Carlos Gomez and I'm going to present the draft entitled TCP Usage Guidance in the Internet of Things. The other authors of the draft are John Crowcroft and Michael Scharf. And the main goal of this presentation is to provide an overview of the main contents in the draft, since, as the chair already explained, our intent is to request a working group last call for this document.
Yeah. Go ahead. State.
So before going into the actual contents, let's take a look at the status of the document. The initial version was presented back in IETF 96 in both TCPM and LWIC working groups. Shortly after, it was decided that LWIC would be the home for this document. LWIC is the working group that deals with lightweight implementation guidance for IoT scenarios, Internet of Things scenarios. And the document has been presented since then at every subsequent LWIC session, and became a working group document, an LWIC working group document after IETF 99. However, TCPM has been kept in the loop through the mailing list whenever there has been any update of the draft, any new published version. Also, a quick heads up on the preparation for the working group last call for this document was given in the last IETF. So the last revision is -04, and again, we intend to request the working group last call. Okay, so let's go into the actual content. So the first section, introduction, provides the motivation and the goal for this draft. On the motivation, we have that TCP has quite often been criticized as a protocol for IoT scenarios. And while some of the reasons might be valid, such as claims on the size of the TCP header or TCP not being a good fit for multicast and some others, the point is that some of the main claims against TCP in IoT scenarios are actually not valid. One of them is TCP being too complex for IoT devices. However, it's actually possible to implement TCP in a quite lightweight way. Also, another typical claim is that TCP underperforms in wireless scenarios. That's true. However, another protocol, which is CoAP, that has been specifically designed for IoT scenarios, also has some end-to-end reliability mechanism built in, and it suffers actually the same problem. It also underperforms when problems in wireless links happen because of this difficulty to determine whether losses are due to corruption or congestion. However, nobody has criticized that aspect in CoAP. So in any case, the consequence is that TCP has quite frequently been neglected as a protocol for IoT. However, nowadays, the situation is that TCP is actually being used in many IoT scenarios, and this could even increase in the near future. For example, MQTT is an application layer protocol that's quite popular in IoT scenarios. It uses TCP at the transport layer. Also, there are some devices in IoT environments that use HTTP. And also, CoAP is an application layer protocol that was designed originally over UDP. However, recently there has been a new version of CoAP specified over TCP. So The goal of the document is providing guidance on how TCP can be used, configured, or implemented in IoT scenarios. So then let's talk about the characteristics of constraint node networks, which are typical of IoT scenarios that may be relevant for TCP. First of all, constraint node networks comprise constraint devices, which are devices that present significant constraints on processing, memory, and energy resources. For example, these devices may have 32-bit, 16-bit, or even 8-bit CPUs. Memory may be, for example, in the order of 10K or a few tens of kilobytes of RAM. And some of these devices may need to live on a simple battery for possibly years. On the other hand, the technologies used by these devices typically offer low bit rate. That's because usually for most use cases in IoT, that's enough, and present high loss rates due to corruption and variable link quality. And that's because mostly the technologies used by these devices for communication are wireless, or in some cases they are wired, such as power line communication. However, also those wired ones exhibit some wireless-like characteristics. Then these devices are connected to the internet, maybe through a router, through a gateway, sometimes through a direct link, or in other cases, there's a multi-hop path between the constraint device and the connection point, the router or the gateway. Then a typical scenario where TCP is being used nowadays in constraint node networks in IoT is the one shown on the slide, where on the left you may have some constrained devices, for example, sensors, that communicate with some unconstrained device, which may be part of backend infrastructure, for example, to centralize the data collection from the sensors. And there's end-to-end communication between both endpoints, which may use TCP as the transport layer protocol. And it's quite typical that also in the middle of the path, there may be middle boxes such as firewalls. Then on the traffic patterns that we may have in this kind of scenarios are, for example, unidirectional transfers, such as a temperature sensor that provides a temperature reading every 30 minutes to the backend, to the unconstrained device. Sometimes there may be also request-response interactions, such as requests performed from the backend and then responses from the constrained devices. And also not so typical, but there exist also some bulk transfers there, for example, for firmware updates for the constrained devices, or when, for example, a sensor transmits a larger file which contains all the readings taken during a whole day. So next, let's talk about section 4, which provides guidance on how to implement and configure TCP for constrained node networks. So this section is organized in 3 main subsections. The first one deals with parameters and mechanisms that relate with path properties. The second one provides guidance for devices that can only use very small window size. And the last one provides more general recommendations for devices that can afford larger window sizes. So the first subsection, path properties, first provides some guidance about the MSS. First, we explain that in many IoT technologies, the link layer MTU is pretty short, in the order of a few tens of bytes or a few hundreds of bytes. That means that in order to support IPv6 on top, there needs to be some adaptation layer, which in some cases includes fragmentation, or in some other cases, fragmentation is supported by the lower layer technology itself. And in any case, when there is this adaptation layer used below IPv6, typically the adaptation layer defines an MTU of 1280 bytes. Then there may be also other technologies used in IoT which support larger MTUs. However, in any case, we explain that for the sake of lightweight implementation, it may be generally desirable to limit the MTU to 1280 bytes in order to avoid the need to support path MTU discovery. A related recommendation is to set the MSS to a value not larger than 1220 bytes in order to avoid IP layer fragmentation. Then we also discuss ECN. We explain that it may be beneficial in constrained node networks since it reduces packet losses and sometimes some of those may only be detected after an RTO expiration, so it also helps reducing latency. And of course, reducing packet losses means avoiding some unnecessary retries, which saves resources which are very precious here, such as bandwidth and energy. Finally, we also discuss explicit loss notification mechanisms. We explain that these are actually interesting because they might allow determining whether a packet loss is due to corruption or due to congestion. However, such mechanisms to this day remain mostly experimental. They have not been standardized and are not widely deployed. Then the second subsection provides guidance for devices that have a low amount of memory and can only support very small window sizes. And for devices that can only support a single MSS send and receive window, then the idea is that TCP may be implemented in just a very simple way with very simple congestion and flow control. There are some mechanisms that are not actually needed in this case. And this leads to some stop and wait behavior, which is, however, often sufficient for most IoT use cases. For example, CoAP with its end-to-end reliability mechanism also works as a stop and wait protocol. One comment is that maybe this stop and wait behavior is not so good for bulk transfers. Then also in this case, there are many TCP options which are just not required, such as window scale, timestamps, selective acknowledgments. Okay, then we also discuss delayed acknowledgments, and we explain that a single MSS receiver, in this case, would add some unnecessary delay to communication. So if that's at all possible, the recommendation would be to disable delayed acknowledgments at the receiver. And on the other hand, a single MSS sender talking to some receiver that's using delayed acknowledgments would suffer this unnecessary delay. And however, there's a known workaround on this, which is called split hack, which is based on breaking the segment in two parts and sending those as two different IP packets, one right after the other, in order to avoid this delay that would be contributed by the delayed acknowledgments mechanism. However, of course, there's the drawback of the additional packet header overhead of this technique. Then we explain that when devices use very small window sizes, most losses may be detected by RTO expiration. Therefore, the RTO algorithm may have a large impact on performance in this case, and this opens the door to considering some kind of fine-tuning for the RTO algorithm, although, of course, this would need to be done carefully.
Gori Fairhurst, could I check what you mean by single MSS, just so that I think I know, but what does a single MSS sender mean? Just one MSS in flight each RTT?
Yes.
Okay. And then you mentioned ECN earlier.
Yes.
And you said ECN marking reduces loss when you have one segment in flight each RTT. Do you want to say more, or should I send comments to you?
Well, no, the point is, well, this section is not only for single MSS, it could be a bit more than that also. So, yeah.
I've read the text. I shall send comments.
Okay, thank you. Great.
Marco, Gori, the answer is that then you avoid retransmission timeout. Yep.
And the ECN text doesn't refer to the latest ECN, doesn't refer to the issues with single segments, and there are other ECN specs you should talk about. So maybe some comments might help the text get better, and maybe the technical things will just work out.
Nice.
Okay, thank you. So then the third subsection provides more general recommendations for devices that have larger memory, can afford larger window sizes. So in this case, we explain that in order to benefit from mechanisms such as fast retransmit and fast recovery, there needs to be a large enough window size, for example, 5 MSS when the receiver is using delayed acknowledgements. Then also we discuss selective acknowledgements. We explain that because there may be losses quite frequently in this kind of scenarios due to the wireless links typically used, selective acknowledgements may help here to avoid unnecessary retries, therefore save energy, bandwidth, and also reduce latency. And also we discuss here about delayed acknowledgements, and we explain that for small messages with a size up to 1 MSS, or when there are request-response interactions, disabling delayed acknowledgements, the receiver would be recommended if at all possible. However, on the other hand, for bulk transfers, delayed acknowledgements would actually reduce the number of acknowledgements. So the best configuration for this mechanism would depend on the actual requirements, the actual conditions of some scenario. Then in section 5, we provide some recommendations on how to use TCP in constrained node networks. So first, we explain that typically, regarding connection initiation, it will be best if the connection is initiated by the constrained device. That's because otherwise, it might happen that the constrained device needs to be listening for always with the read interface in receive mode, consuming energy, and therefore the battery of such a device might be depleted in just a few hours. Then we also provide some guidance on the number of concurrent connections that we may have. The overall recommendation is being conservative. That's because each additional TCP connection will consume some scarce RAM resources, and also having several concurrent connections could be harmful in congested networks. Finally, we talk about the TCP connection lifetime. And first of all, assuming a typical example of some temperature sensor that's sending updates to the backend every 30 minutes, the idea is in order to minimize the message overhead, a long TCP connection is desirable. However, this is unfortunately not always possible because quite frequently there are middle boxes between the two endpoints, such as firewalls, that may delete the filter records quite quickly, for example, after 5 minutes, 10 minutes. And in that case, that would actually break communication for subsequent data packets. So one alternative would be to say, okay, let's maybe establish a new TCP connection for every new data message that needs to be transmitted. In that case, of course, the message overhead is much larger. And the point is that maybe in some scenarios this could be afforded, but in some others, maybe that's too much. So one alternative to that is use of TCP fast open, which would be positive in the sense of embedding data already in SYN packets and reducing message overhead. However, there are also some issues with TFO that need to be taken into account, such as sometimes in some circumstances, some packets being repeated to the application. So if TFO is used, then the necessary mechanisms to take care of this problem need to be in place. There are also other alternatives, such as application layer heartbeats or even TCP keep alives that could be used in order to avoid this early deletion of filter records in firewalls. Of course, then the interval between consecutive heartbeats or keep alives needs to be low enough for this to be useful. However, there's also a trade-off with the overhead that this means in terms of messages, bandwidth, and also energy. So as you can see, there's a number of options here. However, each one has its own pros and cons. Then, for the security considerations, we explained that the best current practice for securing TCP also applies here. For example, use of TLS, if that's applicable. Then we explained that there are some TCP security options, such as TCP MD5 signature or TCP AO, which, however, incur some additional overhead. For example, 18 bytes for the first, between 16 and 20 bytes for the second, and that's possibly quite a large overhead for the typical sizes that are handled in IoT scenarios. Then we also talk about the so-called shrew DOS attacks, whereby one or more sources may generate packets intended to be coincident with consecutive retries performed by a victim node, which would be triggered by the RTO expiration. This is something that may happen frequently when devices use very small window sizes, in the sense that most of those packet losses will be triggered by RTO expiration, and therefore such devices might appear as potential victims for this kind of attack. However, there are some mitigation techniques that have been proposed, such as RTO randomization or blocking the attack by a router based on analyzing the traffic pattern of incoming packets and checking whether it correlates with a potential attack. Finally, we have a section in the document, which is an annex, that tries to summarize the main features of some of the main TCP implementations for constrained devices, for IoT scenarios. The idea is that we try to cover a range of implementations, from those that are intended for very simple devices with even 8-bit CPUs and very small very small memory, to those which are somewhat more powerful. And this is a table that overviews the main features, the main parameters, and whether some mechanisms are actually implemented or not in some of these main implementations. Well, so after the cutoff internet draft submission date, there were some comments provided by Yoshifumi Nishida. Thank you very much, by the way, for the review. So we already provided responses to those comments, and our plan is to quickly publish the next revision, which is 05, incorporating this feedback. So again, since we are not aware of many outstanding issues with the draft, and we believe that it's getting ready, we would like to ask if it's a good moment for issuing a working group last call.
Any comments?
David Black, saw MD5 on one of the slides. Is that still a good idea? It's keep going. It's the security slide 6.
Okay.
One more.
Okay.
Yeah. Is that really still a good idea? I think the security area would tell you no. I mean, if that signature mechanism is MD5 only, it's basically obsolete.
Okay.
If it's only listed as an example, maybe don't list it.
So what?
The sector, you can hear from me now, or you can deal with it when the sector reviewer points out you have a problem.
So David, what's your suggestion?
Oh, okay.
So I think Gory turned up the text, and the MD5 signature was listed as an example. And I think the suggestion is don't use that as an example.
So could it be used in any form, or maybe just?
It's obsolete crypto. It's seriously obsolete crypto. And in fact, rather busted. And if you want to use it here, you're going to have to write a lot of text about why your constrained devices can cope with MD5 and get benefits from it in this special case when it is bad engineering practice almost everywhere else.
Okay.
Gory Fairhurst, I very quickly read it before, and I've had a quick look through now. I'm happy to provide comments and feedback, which I think will mostly be of the style, I see this, but maybe you should think of that. So that indicates it may be ready for a working group last call. I didn't see a summary table anywhere.
It's at the end.
Oh, it's at the very end.
In the annex.
In the annex. I haven't read the annex. I will read that as well. Thank you.
Thank you.
Any comments? So we have some suggestions. Maybe you should update the draft, and then once you update the draft, we can think again, this is ready for working group, let's go.
Thank you.
Yeah.
Thank you.
Okay, thanks so much. Okay, Bob, now it's the time. Okay.
I have to stay on the Red Cross in this room, do I? Right. Okay, I'll move it back here.
Oh, sorry.
Okay, there's quite a lot going on the ECN++ front, which is the name for draft IETF TCPM generalized blah. So yeah, let's get straight into it. One recap slide. What should I do this?
Probably doesn't work, I think.
That didn't work. Okay. Yeah,
Okay, next one.
Okay, so this is a recap slide that summarizes the whole draft. It's actually from a table in the draft, except the second column isn't in the draft. So the problem is the second column, where the original spec of ECN in TCP, which is in RFC 3168, says effectively no, right? Right? Yes. Right at the end, you can put ECN on data, but not on all these other really important control packets. By ECN, I mean the ECN capability. And the proposal comes in two parts. One, if you've negotiated accurate ECN, you can put ECN capability on every packet, just everything, just do it. If you haven't negotiated accurate ECN feedback, which means you're using, if you're using ECN, you must be using 3168. You can't put it on the SYN and the Pyrrhic, but you can put it on everything else, right? And I'm not going to go through the right-hand column. That's all in the draft. And as I said, table is in the draft. That's just a summary of it, but that's the congestion response that you're likely to do. This draft isn't about congestion control. It's just about the wire protocol, but essentially we didn't want to say nothing about the congestion response once you've started putting congestion signals on a packet. So essentially what we usually say is do it like you would do this, sort of a minimal statement of what you would most likely do if you get congestion on one of those sort of packets. But that's more difficult on some of them. So that's a summary, one or two other bits and pieces. When I say accurate ECN negotiated, obviously on the SYN you haven't negotiated anything because you're just sending the first packet. So it means requested in that case in this table. And the two cases with a little 2 by them only apply where you are actually getting the signals, not obviously in the 3168 cases where you're not getting anything.
So this is Richard Jeffnegger. I just wanted to point out that there's a private build apparently for data center TCP where the SYN packet does carry ECT. Yes. So
yeah.
Would that mean that this draft would rule that out, or?
No, not at all. This is the IETF, so you can do what you want if you're not on a public internet anyway, and that's what TCP does. Yeah. And in fact, I've become very familiar with that piece of code, as you'll see slightly later, at least in Linux. Right. Next. Thank you, Yoshi. So we thought we'd finish this draft, but a relatively major editorial issue came up and also 3 technical issues. And that's what this talk is going to be about, which is why I asked for 20 minutes. The editorial issue was that it was, a couple of people said it's really difficult if you're not going to implement accurate ECN to follow this draft. Can you somehow separate out the two a bit better? Because, and I have to admit this was true, we were primarily thinking about accurate ECN, and that was where we put all the effort into writing it, and I admit it wasn't really very easy to do it if you weren't going to be doing accurate ECN. So we've fixed that, and I'll explain that. The technical issues were, it was agreed in the working group that we would allow CE on a Pyrrhic if you're using accurate ECN. And this draft, as I said, isn't about congestion control, but we had to say something. We had to give some hints as to maybe some guidelines on how you might design the congestion control for any congestion on a Pyrrhic. So it's coming to that. And there's the biggest issue in the last few months was a paper actually published by Mia and her friends and a guy that works in Gori's group. Is he in here? Yes, there. That was, no, the study wasn't dire. I mean, the results were dire, you know. And so I'll explain that. And finally, we've had to widen the scope a bit of mission creep maybe to some receiver activities to do with packet validation and acceptance. So all that will be explained. Next. Right, so this first, let's get the editorial issue over first. There was it wasn't just editorial, it was more a process problem in that if you choose not to implement accurate ECN, or because accurate ECN is an experiment in itself, as is ECN++, given this draft has sections that depend on another experiment, it was a sort of queasy feeling that that experiment might change, it might evolve, the final standards track thing might be different, it might even end in failure and all the rest of it. So it needs to be clear what you do without that experiment. And so anyway, suggested solutions from Gori and Michael Scharf were, and others actually, were to either split the draft into two nearly identical drafts, just with slight differences. And I really didn't like that because I hate having sort of identical text, 90% of the text identical and 10% not identical. That's sort of offends my single source type sentiments. The other one was to have an appendix explaining what aspects of the draft depend on accurate ECN, and particularly, actually that's not very well written. I wonder who wrote that. Appendix explaining if you are only implementing the non-accurate ECN parts, which parts of the draft you do. Anyway, we took neither of those. The solution was to actually write it properly, essentially, and to take the sections where there was a dependence on accurate ECN and to split them into two and have, if you're using negotiating accurate ECN, you do this. If not, you do this. And in those sections, every subsection we remind, if you are not doing accurate ECN, ignore this section. If you're not doing accurate ECN, ignore this section. So just to make it easy. Right, and that's that issue over with, I hope. I haven't actually solicited feedback from Michael and Gori as to whether that would solve the problem. I did have a meeting with Gori last time, but not with Michael about it. But I'll let them complain if it doesn't. Next. Right, so, yes, Mia.
Here, Kuhlmann. So I understand the problem of having a dependency on another experiment, right? But I think it actually, so currently the draft says it is recommended to also implement accurate ECN.
Yes.
And part of the editorial problem was also because even if you implement accurate ECN, you might end up with a non-accurate ECN receiver, and so you have the different cases, and those needed to be separated anyway, right? But on the SYN case, when you actually implement this draft, I really think you must implement also accurate ECN. You have to do those two experiments together, because actually it would be much safer to deploy it together with accurate ECN, because accurate ECN provides the feedback you need on the SYN.
Okay.
So I think actually having this dependency
just go back
would be positive.
Actually, I elided a detail on that previous slide. In the SYN section, it says if you are requesting accurate ECN, or not requesting it, because obviously you don't know whether the negotiation is going to happen. On the Pyrrhic side, it's if you have negotiated accurate ECN, then you do the Pyrrhic behavior. So there's a slightly different if in the two sections, right? Because for the Pyrrhic thing, they come after you've done your handshake, right? And so you know you've got accurate ECN, but for the SINs, it's obviously before you know whether you've negotiated it.
So what I'm saying is that you must attempt to negotiate accurate ECN.
Right, I know you are. So I just wanted to clarify that first.
Yep.
But then there are certain implementers who do not want to implement accurate ECN yet, but they do want to do this. And so this is why this draft has that separation and allows them to do that. And then they don't use ECT on the SIN.
And why? I mean, like, I know that this is progressing very slowly, accurate ECN, but why do they not want to implement it?
Mainly all the hassle with middle boxes and all the rest of it. It's a more complicated thing to do than, you know, all the fallbacks and all the rest of it.
I mean, it's so this experiment would be just much safer if you align it with accurate ECN.
I don't think it'd be any safer, because the whole point is, if you are not implementing accurate ECN, you don't do ECT on the SIN, and then it's fine. Everything else is safe, except for the two cases that we've said don't use ECT on this control packet
Okay, so
in order to make it safe.
So the draft says if you don't implement accurate ECN, you should not use it on the SIN.
Yes.
Okay, that's okay. Sorry, then I misread it. Okay, that's fine.
Yep. Right. As the recap first table said. Right. But that's fine. That's fine, because I often don't look at other people's slides either. Yeah. Right. Okay. Pyrrhic congestion response. Now, there was a lot of controversy about this whole area. So I just want to get into this slowly so people can all understand it. The problem is, if you're going to put the ECN capability on Pyrrhics, that does two things. It protects them from loss, but it also obviously tells the receiver if you've had congestion on that Pyrrhic. And a congestion mark on that Pyrrhic doesn't necessarily mean that Pyrrhic itself was causing congestion, but it's on a congested path. Right? Then the question is, how do you respond? And that's in two stages. How do you feed it back? And that's not in scope of this draft, because that's the feedback stuff. But then if you get the feedback as the sender that originally sent that ACK, what do you do with it? Right? So, as I said, congestion response specifics are out of scope, but we have to say something. On most of the control packets, we can just say, use the usual congestion window or initial window response, which is what we do. We make up some stuff on the SYNAC case, but the Pyrrhic is a difficult one, because partly because there's a lot of confusion in this area, which I'll try and deconfuse, and partly because it's difficult. So ultimately, the specifics need to be defined for each congestion control, because this isn't a congestion control document. But if I now give you some ideas and guidance, and see what you think of this guidance. So even if this guidance is wrong, it doesn't really matter, because it's not normative, but it shouldn't be completely wrong. So let's go. Yeah. Right. A CE marked Pyrrhic is part of an aggregate causing congestion. So the first thing to say is that if you've got this model in your head that there's a server blasting data down at some client, and the client is sending a Pyrrhic stream back with no data in it, and it's getting a CE mark on some of those Pyrrhics, that isn't necessarily the whole story. Number one case, there may be another flow, either from your own machine or someone else's machine, in the upstream next to that ACK stream that is causing congestion. Say someone's uploading a video to YouTube and your ACK stream is congested by that. So it doesn't necessarily mean your ACK stream's got to slow down just because it's getting congestion, but you have to do something, right? So that's the idea is that of these pictures is that's the gray case. You're the red case, the ACK stream with the little dots, and the gray is something else, right? Something big next to you. It may be that your own flow is also sending data interspersed with the ACKs. When you get a congestion notification on the ACK, you don't necessarily want to add all the logic to say, am I sending other packets or not at this time and all the rest of it. You want to be able to know something brainless to do. And the third case is the one that everyone's assumed up till now, which is if you're getting CE on ACK, it means you're only sending ACKs, and that's not necessarily the case, but it could be. Right? So in the draft, informative only, we suggest two potential responses. One, very optional, if you can have very optional, and that is to use the ACK congestion control RFC. And the reason that's optional is quite complicated for what it gives you, but that is a way of slowing down the ACK stream or increasing your delayed ACK factor, essentially, because you can't slow down the other end. And then it also suggests that you reduce your C-wind, even though it's a pure ACK with no data on it, proportional to the sum of the CE marked header bytes and the CE marked data bytes divided by all header bytes plus all data bytes. In other words, the sum of all your CE bytes divided by the sum of all your bytes. Right? Taking a nominal header size, so you can guess a header size. Yeah.
I didn't get it, Bob.
Okay. Right. On a round trip time. Right. So imagine this is.
Marko, neither did I. So,
Yeah, okay, right.
one clarifying thing for the response, are you now talking about the receiver of the pure ACK or the other end? Who
I'm
sent
talking
the
about
pure
the
ACK?
sender of the pure ACK.
Why should that bother at all? Because it's ACK, and you are sending data.
Right. What this is about is if you're putting ECT on a pure ACK, we have been asked to make some sort of congestion response if you get feedback saying there was congestion marks on that pure ACK. You can't necessarily. Yeah,
So why
Mia's
would
the
you
one that asked us. So.
Mia Kulevin, there are two cases. One case is you've been sending data, so your congestion window is actually big, but you stopped sending data and you only send pure X now, but you get the congestion feedback for the pure X. Should you now reduce your big congestion window based on that feedback? That's case one. And the second case.
So the sender of the pure X or
the receiver? The sender of the pure X, you're the sender, but you've been sending data, and then you. No, you've been sending data. You sent data. Now you're the sender. You sent data. You stop sending data, but you still send ACK because there might be data flowing in both directions. So at that point where you're only sending X, your congestion window can still be big because you've previously sent data, and now you get a congestion marking on the ACK. Should you reduce your congestion window?
In case you start sending data again. Yeah.
And the answer is yes, but how much should you reduce it? Right. That's the question. And the second case is also if you're sending, which is addressed by this, but might be similar. If you're sending data and X at the same time, right, and you get a marking on the ACK, does it have an impact on your congestion window?
Okay, so the idea of this formula is essentially that you scale down your congestion response by the size of the packet, and obviously because an ACK has no data in it, you could say it's got size 0, but it hasn't. It's actually got a header, and so what this does is effectively say, well, let's make the proportion scaling be the size of the ACK packet divided by the size of a full scale packet. Full size packet, including the headers in both cases. And so with accurate ECN, you can do this quite simply. You've got to count all the packets, but you have to guess how big your packet headers are unless you can actually know it through your operating system somehow. But I don't think it's a particular problem guessing it. You just guess 40 bytes or something. And it doesn't matter too much if you're wrong, because this is a fairly arbitrary scaling anyway. But it just means that if you're getting a mixture of some pure ACKs with CE marks in some full-size segments with CE marks, you take the total of all those over a round trip time, and therefore if you're sending a lot of pure acts, they won't make much difference to your congestion window. And if you're sending a lot of full-size segments and you get 1 or 2 pure acts also marked in there, they'll make, you know, the marks on the bigger packets will make obviously a lot more difference. But it will eventually, and if you're sending a pure act stream that alone, that means your denominator, the total number of bytes, is sort of also small. And so that will effectively just give you the fraction of ECN marks in ECN mark packets. Right?
Yeah, Kuhleman again. Remind me, what was the problem about just having the window or whatever applying usual congestion control in that scenarios?
Well, if you halve the window because of a CE on one act, there was a complaint on that, and it's a very valid complaint, that you're being very unfair on yourself, because if you then start sending data again, particularly in the case where it's not you, you've just massively reduced your congestion window, even though you weren't sending anything apart from your acts because of something else's congestion. And so the idea is to scale it by the amount of data you're sending. And if everyone's doing that, it should then end up that you don't hurt yourself. You know, basically, you're shooting yourself in the foot if you reduce by your congestion window by half because of a CE on one pure act. You know.
Magnus Westlund, Ericsson. Doesn't this require you to do more accounting than you did before on what data is?
Yeah, well, that's why the previous slide said this all depends on which congestion control scheme you're in.
Mm.
And this is a suggestion as a guideline that the particular congestion control algorithm will make those trade-offs, but we can't make those trade-offs for them all. So this is, I would say this, because it's related to accurate ECN, it's more likely to be for data center TCP type things than your traditional big response to one.
Yeah, I was just thinking about what it would mean to apply this, for example, to the quick, etc. But it might be, I mean, that's the current V1 is Reno style, etc. So
you'd have to come up with something else for a Reno style congestion response. I'm just assuming that we're not really that interested in keep on updating Reno, because not many, you know, it's becoming less and less used and all the rest of it. So the focus is, my focus certainly is moving away from that.
So Gary Fair has just an observation. Is this a bit like the CWV story we went
through?
Yeah.
And in fact, in the draft, it says that you would have to work out some way of integrating this with CWV so that if you're doing congestion window validation, essentially some CE marks on your act stream mean you would reduce it faster. Your CWV would be reduced faster than if you weren't getting CE on your act stream. So this is only, it's just sort of enough to get you through some. It gives you some ideas on how you would do this, but it's all got to be done properly in a congestion control draft. And so I can see Mia looks so happy about this. I think the size of her mouth about 3 centimeters below the middle.
I understand that this is like not any kind of normative requirements or whatever, and this is part of the experiment, and providing some hints does make some sense. But like this is very, very close to data center TCP style reaction, right? So it's like it's a quite specific case after all. So I'm not sure if that's the case that I would recommend in general. I don't know.
Okay. I don't know how to do it for a Reno style thing, because I mean, like,
the answer of the experiment could also be that you just want to adapt the CWV stuff slightly and take ECN into account, or the answer could be just
Yeah.
half, because the cases where you hurt yourself are very rarely and they don't really hurt, or whatever. I mean, that's part of the experiment, I guess.
So, right, go on.
Marco, so am I understanding correctly that in this case 3, you do nothing?
It will end up, you still reduce your congestion window, but it has no effect because you're not sending any data.
Exactly,
Yeah.
but that's the case where I see that you should do something because you have act congestion.
And so that's the optionally at congestion control would be possibly that, but the trouble is you don't know which case you're in.
Exactly, but
So
would be
the
all.
idea is to do something that will that will deal with this reasonably, and ultimately, if you are in scenario 3, and your own ACK stream and maybe other ACK streams are the thing that's congesting this link, ultimately, if your lack of action causes that congestion to get worse, the ECN will move to drop in the network, and it will start thinning out the ACK stream, and that will sort it out.
But then it should get very, very bad.
Well, it's just like ACK thinning.
Yeah, this not much thinking of this. But
no, I don't think it will get very bad, actually.
Yeah, but I have not been thinking about this a lot, but the case 3 would be the only case where I would react, and I wouldn't bother reacting in one or two because they are sorted out in other ways later on. And, and now if you try to kind of react, this becomes very, very complicated, and you would have side effects in different scenarios, and I would like that.
Maybe another way to put this is that this is a way of saying when you're doing congestion window validation, if you've got some information, use it. Is another way to say this. You know, you're getting more information.
Yeah, you would use that for the congestion window validation, but not kind of reacting with your congestion window.
Well, congestion window validation is altering congestion window. You know, that's what it does.
But in specific conditions.
Yeah, but that's the case here. We've not got any data. We're not actually hitting the congestion window necessarily because we're just sending pure ACKs, but we're getting some feedback.
Okay, but then as a bottom line, this sounds way too complicated to optimize a last corner.
No, the idea of that formula is, I mean, that would be really simple to do in data center TCP, for instance. It's just slightly changing.
I'm not meaning only that, but that you would kind of send the feedback to the other end on those pure ACKs.
No. Okay, this doesn't go into that, but Accurate ECN already sends that feedback because it just sends a counter of how many packets and how many bytes you've had with congestion marks on them.
But I didn't see that the Accurate ECN was required for pure ACKs.
Correct, yeah. But it is required for, it's required for pure ACKs and SINs. If you want to put ECT on a pure ACK, you have to use Accurate ECN. Or put it another way, if you're not negotiated Accurate ECN, you must not put ECT on a pure ACK. That was in the table at the start as well. They were the two cases, the SIN and the pure ACK. Yeah. Right. Okay. Right. So just to finish this slide, it deals reasonably with all three cases. In 1 and 2, you get a congestion window reduction that's scaled down a lot by the fact that you're getting congestion on, markings on very small packets. It deals with 1 and 3 in that you get a congestion window reduction, but it has no effect on the pure ACKs, which is maybe what you want. And the ACK-CC one would deal with the ACK stream, but I think just ACK thinning by loss deals with that sufficiently. But it's all experimental. I don't think there's been enough work to understand this. And the other thing I have to say about this is that we've not had ACK congestion control in the internet for the last 30 years, and it all seems to be okay. You know, you know, to add it now seems a bit sort of anal. if I can use that word. So I'm trying to do something as simple as possible, or at least to suggest something as simple as possible for the accurate ECN case, and I would hope that gives the hint to people to do something as simple as possible in the other cases as well. And as simple as possible might be nothing, but I can't say that in a draft. Right, next. Okay, so moving on. You have to read this title like you're a football score, reading out a football score. Network mangling 0, server mangling 84. Actually, it's more like a rugby score, isn't it? So I happened across this paper and then discovered it was written by Mia from this June, and Ian and so on, and Brian Trammell. And it got me very embarrassed, right? Because we've been doing measurement tests, and so has Mia for some years, and Ian. Of the 82% of servers that now support ECN, so really cool, we've got up to 82%, but 84% of them will disable it if you send them an ECT SYN. Right? Okay. Right. Now, how did we never discover this? Partly because I thought the student understood that this is what they were meant to be measuring, and in their report, I thought they had measured it, but they hadn't. And Mia confirms also that in all their previous experiments, they haven't measured the server's response, they've only measured the network's response, and same with us. We've only checked for network traversal, we've not looked at what the server does with it. Really embarrassing, right? Anyway, I traced it, at least, obviously I can't know, well, we could know what the operating systems of all these were with a lot more work, but assuming this is Linux, I traced it to a patch applied in May 2012, and there was that comment on top of the patch, which says it all really. It says, RFC 3168, there aren't many comments in Linux actually, but it says, SYN packets must not have the ECT bit set, so therefore we assume that if they are set, the network must be mangling things. So from one end, we make an assumption. Therefore, if the client starts setting these bits, we still assume the network's playing games. I'm going to call this the contra-postel or postel test, just to give it a name, and I'll explain why on the next slide. So how do we get this fixed? Well, let's just have a bit of irony first. In our measurements of network mangling, which unfortunately were the only ones we did, we've actually got to the point now where we found 0 occurrences of this problem where a not ECT SYN becomes an ECT SYN or a CE SYN. Can't see it anywhere. But Linux is testing in case it's there and turning off in 84% of cases all ECN if it is there. So it's a rather drastic action based on a one-ended inference of a co-point transition. And it's also silent, so there's no logging of the problem to get it fixed or anything like that. So I would recommend, or we recommend in the draft now, which means we're saying the IETF will recommend, remove that test, the contra-postel ECN test, while you're deploying accurate ECN on servers, and that's why are we saying this in a draft that's about ECN++, and that's because accurate ECN does a two-ended test of this mangling, which is a reliable test because you're getting one end to ask the other to tell it what it saw, rather than just assuming that these bits have been changed by the network, rather than so you know what you sent as well as what the other end received. So certainly that's already in accurate ECN, so that's the first recommendation. Now, you could also recommend that while deploying ECN++ on servers, that you get this test removed, or you could just recommend that everyone removes it, and particularly given the network doesn't seem to be doing this anymore, that could be safe. But I assume the reason it was originally put in Linux was because they were worried that if the network was turning 0 ECN into ECT or CE, then your ECN mechanism wouldn't work once you'd negotiated it, because it's probably some diff-serve bug in some bit of network equipment. Yeah.
Mia Kühlewind again. So there was the case where the ECN bits were overwritten to be set to CE, which actually had the consequence that like every packet was congestion marked and your throughput goes down to 0, right? And so that's why they had the fallback. I was also surprised to see that they had the same fallback for ECT 0, which seems to be wrong.
Yeah, and partly through Apple's deployment and fixing of that problem, this does seem to have gone away very quickly, and to 0, well, from as much as we've measured, you know. And it's actually also difficult to measure when we measured it on mobile networks, we had a lot of bleaching of the ECN code point, and therefore if it wasn't bleached, you might find the things happening behind that bleaching. So we don't actually know, you know, there may be 2 effects on the same path, one of which is hidden by the first one.
Michael Abrams, so the quoted text, I tried to find it here in 3168. Did they get it wrong, or are we actually
No, the reason this is called the contrapostal ECN test, or I've called it that, is that 3168 says the sender must not set ECT. And that was interpreted by the Linux folks as, if we receive one, it must mean that something in the middle changed it, not that the standard changed.
Okay, so 3168 is silent on this matter.
Oh, the silence is that 3168 doesn't say what a server should do if it gets one of these packets.
So should we update 3168?
That's next 2 slides. Two slides on. Yeah. Right. Okay. But this is just how do we get the code fixed? Is this slide? In fact, number 3 there is fix the specs, right? Which is well, I said it's 2 slides on. So the next slide is a workaround by client caching, and all this was actually already in this draft, because you have to do this caching anyway for, this is essentially the test for whether the other end supports accurate ECN. And if it doesn't, then don't send your ECT in future to it on the SYN. And there's 2 possible cases, both identical diagrams, except everything's flipped in one or the other. In other words, the default is set ECT on the SYN and turn it off if it's cached, and this one's don't set ECT on the SYN and turn it on if it's okay. You know, that's essentially what these 2 diagrams say. We're still recommending that as the should in the draft. In other words, be optimistic, turn it on to start with, and then see if it turns off. But of course, if you're wrong, which you will be in 82% of cases at the moment, that will turn off ECN on your first attempt, but then it will get it right on the following attempts, right? And that is on the basis that a lot of your flows are, you never go back to that server, but once it's in the cache, you know, you'll have a cache of a certain size, and it will pick up the most popular ones, if you like. Yeah. But we can argue in the working group which we should recommend, but it will be up to implementers anyway to decide how they do their caching anyway. It's not an interoperability thing. I'm not going to go into any more detail on this slide. This is all in the draft. It was just an attempt to explain it reasonably quickly. I think the only thing to say about this is that probably the most significant aspect is to decide between these is what happens to if you don't want to have too big a cache, particularly when you've got this large percentage when you start of servers that are problematic. You'll have to have quite a large cache to catch them all. So what I would suggest is you don't have a large cache. That just deals with your popular stuff, and then your default is something you're prepared to live with. If it's not in the cache, or it falls out of the cache, gets expired or whatever. Yeah.
I would say if we get the code in the Linux kernel fixed, even so it will take a while until it's deployed, we should go for the first option where you set it on the SIM.
Yeah. Okay, next. Right, so fixing the specs. 3168. This was. I wouldn't quite say it's the problem. The problem is the silence on what to do if you get one. So the host must not set ECT on a SYN or a SYNAC. 83.11, which David produced as an update to this, has added, unless otherwise specified by an experimental RFC, which is what this draft is, and that was what it was intended for. So that's a bit opaque for the Linux community to determine that first statement is no longer true. And I did actually argue with David at the time that we ought to make this clearer, but David didn't want to make everything non-compliant in one swoop. However, we could have said, it would have been nice to have something in 83.11 that had a clear statement of at least a should, so that it was clear. It's a bit difficult to argue with the Linux community when we haven't really got a clear statement, because on that third bullet, what does the server do if it receives non-zero ECN on a SYN? 3168 says nothing, 83.11 says nothing. 83.11 does say what a middle box shouldn't do, but David didn't want to say what a server doesn't do. So you could interpret silence as default to the robustness principle of John Postel, which is where I got the name for this test, which is be liberal in what you accept, as opposed to what Linux is doing, which is being conservative in what it accepts. But that's the Linux community's prerogative, because nowadays you can't necessarily be too liberal about what things are going on networks. No, the must is the other way around. The must is what the sender must do. Yeah. It doesn't mean to say the opposite won't happen somewhere else. Right. So what I've put in this draft is, in order for this experiment to be useful, the following requirements follow from 83.11. In other words, we now have an experimental draft. And so this experimental draft says that any TCP implementation should accept receipt of any valid TCP control packet or retransmission, irrespective of its IP ECN field. If any existing implementation does not, it should be updated to do so. And that should is so that you don't invalidate everything. And if a TCP implementation is taking part in this experiment, then it must do that. It must accept all of these. Right, David.
David Black, this one may rattle quick, in which case I will sit down equally quickly. Okay, so the second bullet is kind of obvious, which is that if you're part of the experiment that's experimenting with ECT uncontrolled packets, and then you bloody well better accept them. First bullet is, it enables the experiment to be deployed, and to be deployed with a mix of other things. So I think I get that one. I'm not sure why you're anchoring this in all of this in 83.11, as opposed to anchoring it all in the structure of the experiment.
Okay. Primarily because 83.11, it was really 83.11 that modified 3168.
Oh, I'm agreeing 83.11 allows, Gory's comment was 83.11 modified 3168 to allow experiment. Absolutely true. What's bugging me is the three words that basically say these requirements follow from, i.e. are implied by 83.11. I don't think those three words are quite right. Follow from RFC 83.11. I think the requirements are inherent to the structure of the experiment.
Right. So I guess what it means is, or what I ought to say in there then is, given we now have an experimental ROC, the following experiments follow from ROC 8311 or something. Yeah.
Well, the following changes take advantage of ROC 8311.
Corey Fairhurst. I did the Abe thing, +1. David did that to me on the Abe draft. 8311 allows you to do this. You define the experiment the way you want it.
Okay, well, let's sort out wording on the list, shall we, or something like that, but, yeah.
Does it actually update 8311 or no? Then actually, I don't understand the point about the sentence at all, because just because you write it in this draft, the code will not change, right? So.
No. So it's more, the idea of this is that we've got something, when we have an argument, if we have an argument with Linux people, if there's any pushback, then it would be useful to be able to say, we have changed the spec.
Yep. So I would actually suggest a short, like a separate RFC that updates 8311. But they're basing it off of the 3168.
No. This is what we got up to complain about. Between Gory and I think what we're telling you to do is strike the words "follow from 8311" and say something like "are necessary," because 8311 doesn't imply any of this. It opens up the opportunity to do so. And your assertion that you need these requirements, I think, is correct. But the assertion should be grounded in the structure of the experiment, not the window that 8311 opened for you. And the response to Miriam's question is, Bob left the baseball bat background off behind this new text.
I don't know about the baseball bat thing. I didn't understand that. But no, it wasn't I understood the sport. I just didn't understand the.
Okay.
I think it's important to keep something in about RFC 8311 and link it with the fact that there is now an experimental RFC. Yeah.
So in order to get that code out of the Linux kernel, I think you need to have, okay, this used to be in 3168, there is now 8311. You need to have a clear trace of something goes out to say.
That's what I'm trying to do.
Yeah, exactly. Yeah. So this is what I'm saying, because you need to actually motivate this patch. And I would say, okay, try the.
I would disagree with you that RSCs don't motivate them, because RSCs motivated them to put the patch in the first place. That's the problem. It's in the comment. It's very much. Yeah. We're doing this because the RSC says.
The patch. There's a patch comment that says 3168 says this. This is why the code is here. So frankly, you can try. And if you fail, I think we should tell them we need to actually update 31 or 8311 to specify that this is the way it should be. But you can try first with just this text and see if they can accept the patch. But if they won't, we might have to do this again.
Yeah.
Huh?
No, but that doesn't say that.
Bob, I think we should have a very small conversation afterwards. Okay. This is a semantics of a few sentences.
Right. Yep. I'm happy wordsmithing offline. Right. Next. Right. Okay. So then, having written that into the draft, we realized that the draft now said in a number of places this is a sender-only change. ECN++ is a sender-only change, and now we're starting to talk about receiver stuff, right? And so what we realized we actually meant was this is a sender-only deployment, and we had in other words, you can deploy this sender-only, and there are these guidelines for when you receive these packets of what to do, but it doesn't stop you deploying it as a sender. You don't have to negotiate it with the receiver, right? And so we altered all that to say it's a sender-only deployment rather than a sender-only change. And we've got a new section where we've collected together all the things you do on the receiving end of these packets, rather than having it sort of hidden in the section that says this is all about senders. Because there's already stuff in there on, packet validation checks. I think it's 5290, is it, or something? The one that does all the checking for DOS attacks on packets and stuff like that. There's already all those sort of recommendations in as well. So that all goes with this. Next. Okay, so we hopefully really have finished. I mean, there's obviously some work to do outside of the IETF now. But closed off those 4 open issues, restructured the writing. There's a huge amount of edits in this latest draft. Got some suggestions on response to CE, got the stuff about the test in there. And I've tried to keep the normative part of the draft really short, and I've moved out even more into the informative part of all the rationale. So to know what to do, you've just got to read a fairly short amount. And so I think we're at the point now where we can go to working group last call. And it's incredible how difficult it is to just set a couple of bits, or even one bit.
But we have lots of comments, right, on this draft. Maybe we should update the draft, I think. You should update the draft.
Update it?
Updates.
Well, that's true. We've had, I think there's a wording change on this particular thing on 8311. There may be some discontent about the Act congestion control. The other 2 bits. But is there anyone actually wanting us to change that Act congestion control stuff? I guess people maybe have people read it?
Okay. How many people read the draft? Could you raise your hand? This version? No. Because this, okay, previous version. Yeah, because you have changed a lot in this version.
Yeah.
So maybe we need some time to keep us ready.
Maybe we can go.
And you can have local discussion during this meeting, and then you can have a good idea how to update the draft, I think.
Yeah. Also, hopefully during this meeting, I'll now get in touch with the guy that did this was actually Eric Timothy, and see if we can see what response we get.
Okay.
Okay.
Yeah. Thank you.
Can I make one suggestion? So usually it's because it's an experimental draft, it's nice to have a section that actually explains the experiment. And then actually the text about reacting to CE markings on POX could actually go into the experimental scope part.
Yeah. Okay. Can you put that in an email quickly, or write it down somewhere so I don't forget that? Yeah. Okay.
Okay. Move on to the next one.
Which I think is me.
Okay. Yes.
Okay, so do I have to go faster, or do we have much time? Or
You still have nearly 30 minutes if you want.
Right. Now I'm aiming to do this in 10 minutes.
Okay.
Right.
Up to you.
Thank you. Right. Oh, yeah. Let's just stick on this further. So this is a similar talk to one I gave in TSVWG in Montreal last IETF.
Sorry.
Oh, sorry. And it's about how RAC gives an opportunity to remove head-of-line blocking from links, particularly radio links, but all links, where you know that it's being used with L4S, and there are other cases, maybe even all UDP. So if you like, you can think of this as one of the reasons for deploying quick is to remove head-of-line blocking, but maybe we can remove it from TCP as well. Right. Next. So I don't need to give too much background on RAC, hopefully, in this group, given it's a working group draft in here, but I'll quickly give a brief. Loss is when a sender deems that absence has been long enough, right? The sender or the receiver never knows whether there's actually been a loss. And obviously with classic TCP, you have the 3 due back rule. With RAC, the idea is either a fraction of the round trip time, or you actually measure, later on when you've got an idea of the reordering window that you're seeing, you measure it and you determine what the reordering window is. And I'll call that, I'll measure that as a fraction of the round trip time and call that epsilon, which Greek people would call it, or mathematicians. So there's a trade-off here. If you have a larger fraction of the round trip time before you deem there's a loss, that minimizes spurious retransmissions, so it improves your throughput efficiency. But if you make it smaller, if you make it larger, that also means it takes longer before you repair any losses, because it takes longer to deem there's been a loss. Now, if you're already going to lose a round trip time, you can't know there's been a loss in less than a round trip time. So you've already got 1 times the round trip time. With epsilon weighting epsilon of a round trip time more, you get 1 plus epsilon. So if epsilon is like an 1/8 or a 16th or a quarter, or whatever, it doesn't mean you're significantly waiting that much longer. If it was 75%, 90%, you're getting close to 2 round trip times, so it's starting to quite seriously impact your delay. But as long as epsilon is a small fraction, you're reasonably okay. But you don't want to go too small, otherwise you start increasing spurious retransmissions, because you start getting under the floor of reordering in the network. So RAC actually adapts its reordering window. It starts small, and at the moment the code just starts with the 3 due back rule, and then it starts to measure the reordering degree. So next, details are in that draft. So this talks about the combination of L4S and RAC. So I'll quickly recap L4S for those in the room that don't know what it is, because it's only partly related to TCP. The idea is for really low queuing delay for all internet traffic, including saturating traffic, TCP-like traffic. So you can have new high applications like VR and all the rest of it, high bandwidth applications that still keep you a really low delay. And by really low, I mean in the hundreds of microseconds, which is a couple of orders, 1 or 2 orders of magnitude better than the current state of the art with FQ, CODL, and Pi. And you may have seen some demonstrations in the IETF of applications with that sort of very predictable low delay, high bandwidth applications a few IETFs ago. I won't go into the architecture of L4S, just to say that it's a protocol change on the ECN field. It uses the ECT1 code point to say this is an L4S packet. That's all you need to know for this talk. And then it uses a congestion controls in the same family as data center TCP, which is what gives the low delay. Right, next. So about 3 months ago, we realized there was an opportunity here. So we added a 5th requirement in the L4S spec. There are requirements on senders on what they must do in order to have the right to set this code point, because essentially the low delay in L4S comes from the sender's behavior. And the DCTCP-like congestion control is one of the main things that gives you this very low delay. And we realized if we added one more requirement, this 5th requirement, that you must not detect loss in units of packets, we would get a very important gain for the future. And so this talk is about whether that is a sensible idea. and whether there are implications. So what it's really doing is it's releasing a constraint on link designers so they can make faster links, but it's giving you a bit more pain in the sender, in that you have to do this rack thing, which has already been done by Microsoft, Apple, Google, but it's not quite like the rack I'm talking about here. So really the pain or the permission to do this has to come from those who would have the pain of implementing it, which is TCP, RMCAT, all the congestion controls. And then if we do that, I'm now going to explain why that gives you benefits in the link end of the architecture. And this is all explained in that appendix of the draft, if you want to go and read it. Next. So the idea of saying must not in the L4S specs, you must not count in your 3-dupack type rule in packets, you must do it in time, is so that any network link that sees ECT1 at the IP layer can know that there's nothing that's counting in packets, and that means it can disable all the effort it's putting into making sure that the packets stay in order in the network, right? For that particular, if it's got a queue where all that traffic is, and in this case L4S has a queue where all that ECT1 traffic is classified into, and that means it can turn off resequencing, and that can give you quite significant gains. In a radio network, what happens is you have your link layer retransmissions going on, and at the receive end of the radio link in LTE and Wi-Fi, it will buffer those packets that have got through until it's got all the link layer retransmissions through, and then it will send them once it's not got a hole in front of them. So you get head of line blocking because of that need to keep things in order, because of TCP's need to ensure that not more than 3 packets are out of order. And so if you can turn that off, you can remove all those delays from your radio links. And it's not only radio links. Most attempts to make links go faster these days involve spreading your capacity over a number of bonded channels. And so you're running over multiple frequencies, and then at the end they all have to come back together, and so they all have to wait to get back in order. It just makes the whole thing more complicated. So if you just release things as they come, or at least where things is packets. And so this must not means that you can know that you can turn that off. Now we've got rack in TCP, you can't turn off your resequencing because of course there's still all the old TCP in that queue as well. And so that's going to take decades until that's removed from the network. So the idea here is we've got a new queue. If we can say you must not do the old things in this new queue, we can immediately get the advantages. Right, next. So let's try and explain why this is an advantage for links to not count in packet numbers but in time. So this diagram, this doesn't work at all. Does the pointer work? Yes, it does. Yeah. He says looking down the end of it. Right. So here you've got a slow packet stream, and here you've got a faster one, 96 packets per round trip time versus 12. And so your packets obviously take a shorter time as you go faster. So 3 dupacks becomes a smaller and smaller amount of time as flows get faster, right? And so that means that all the engineering you have to do to design a link has to be done in a smaller and smaller amount of time the faster you go, which makes obviously making a link faster means you've got to do things in a smaller amount of time, but you want to do less things. And so having to ensure that you keep everything in order in this very small amount of time. Sorry, I've lost it now. Like we're down to 750 microseconds, then that's only 96 packets per round trip time. If you go 10 or 100 times faster than that, you're down in the single microseconds and so on, that you have to keep everything in order. And so if you're got a multi-channel link, you've got to hold everything and get everything back in order to that level of precision. And similarly, these link layer retransmissions, it means you've got to be holding everything and make sure it all gets back in order before you send anything, because you haven't got any leeway with those sort of small amounts of time.
Very first. Or you ensure your mapping to the links is ECMP-like, where it's deterministic, that you don't create reordering within the flow.
Yeah, but
which constrains your options and the capacity, etc.
Yeah, and yeah, some link designs it doesn't matter, others it does, but you know, at the transport layer we don't know which links you're on. You know. Yeah. Okay. Next.
Okay. So quick question. So you mentioned rack here, but it's actually timer based because rack sometimes fall back to the debug.
Yeah, I'm coming to that. Yeah.
Oh, okay.
Yeah. Yeah. So yeah, I said this already, that with a radio link you can just send from the straight from the receiving end of the radio link without the resequencing buffer, and then the end system, you know, the TCP receive stack will put things back in order rather than you putting it back in order in the network first, and that's because the network has to stop TCP thinking there's been a loss, and also. Sorry, I had a thought in my head, but it's gone. Anyway, right. So next, yeah. So this is the discussion point, that if we say in the L4S specs and potentially in Quick as well, although maybe the horse has already bolted on that one, because then you could say all UDP you don't have to put into order, which is generally assumed at the moment, but you know, yeah, okay.
So I would just before, like, I know UDP applications. So, you know, the things that programmers believe are true, one of the things is UDP packets are delivered in order.
Yeah.
I know people who assume that.
And that is the case in things like RTP over UDP.
Yeah. So, Magnus Westlund. I'm not certain I fully understand what this actual constraint here is, and what's the issue with packet counting really is, if it's just ensure that if you properly account for it and know what it is. I mean, but yeah, it can be sender side by counting, can't it?
Okay, so maybe I didn't explain then.
Well, that's quite. No, let's skip that. But yeah, it's. I think we probably. I mean, we could take that offline. But anyway, I think we need to have not over constrain this in that sense, so that we can actually have something as reasonable as possible.
So not over this.
Not over constraint. I mean, if you're really saying that this is more strict than rack is, why? I mean, it's.
No. What I'm saying is that if we can use rack or a rack-like system to the extent that we can require it for L4S, then it removes the constraints from networks on that queue.
That's, and I don't see the problem, for example, in Quick as currently specified, except for ECN, with correctly accounting for what's actually been marked, etc. So it's. I mean, we need a little tweaking there, but even in that sense,
we're not talking about ECN. We're talking about loss detection.
Yes.
Yeah.
And if you do loss detection, I mean, Quick will know what it lost. It has a count.
But it's the question of Quick.
Yeah.
The very first thing I said in these slides is the transport layer never knows whether it's lost anything ever.
No, but it knows it hasn't been delivered.
Might have lost something.
Yeah, it's
how much time or how many packets it takes to know that.
Yeah.
Right?
Yeah, and that information Quick has as accurate information as possible. It knows which packet's been reported as received.
No, it's not. That's not the issue.
And how much time has been. Yeah.
What it uses as the metric for deeming that it's had a loss. Does it count in packets or in time?
Okay. And that it can clearly do both.
It can.
Yeah. And it has to do with the congestion control implementation only.
But I don't believe currently you've got a rack-like mechanism in Quick, but I may be wrong.
Christian Wittema. Bob, I like your talk. I like where you're going. What you're going is that there is a lot of crap in the network that is there because there was a lot of crap in the transport. And so if we gave the network guys confidence that there is no more crap in the transport, they might remove the crap in the network and we might have better network. And that's nice. That's very nice. Now, the point is that it will take some convincing and it takes some time, okay? Suppose that I am at the cable labs, for example, deciding whether I want to remove the resequencing in my packets. And there's Bob here explaining, hey, if that bit is set, I mean, you can. Or if it is UDP, you can. And you will have an old crusty guy that says, no, these transport guys are bozos. I mean, if you do that, it's going to break. So how long will it take? How long will that process take so that the old crusty guys acknowledge that maybe they don't need to do that?
Right. I don't know how to answer this because I'm under an NDA. But
because that's what you're saying. That's exactly what you're saying, okay?
Yeah. I'm optimistic, put it that way. From my experience, I'm very optimistic.
And the other thing about Quick, I mean, there's one part about Quick that goes in your relation, is that Quick actually encrypts the packet sequence number.
Right.
So it's really, really hard for the network to put the packet back in sequence.
No. It depends,
Okay.
It depends on the link sequence number. So if they've got out of order when they arrive at that link, it will keep them in the same order at the other end.
But so basically what you're proposing is that we remove the crap in the transport, which is generally a good thing, and we hope that sometime there will be fewer crap in the network.
Yeah, and in fact, we are already removing the crap from the transport. What I'm saying is, well, let's mandate that it's removed from things that can identify themselves as being removed at the network layer, so that the network knows they've been removed.
It would make a lot of sense to say that if you do rack, you don't have to do DPAC.
Yeah.
It would make a lot of sense in general if we could do that, because it will make everybody's life better, and it might eventually start that process that you're advocating there.
Yeah. And it's not only a mic, it's because there's a lot of pressure from link designers to not have to do this. So I think your pessimism about how long it will take them to change. I'm more pessimistic about the fact that they will take the brakes off too much and allow too much reordering because it makes their life so much easier.
Oh no, they have no the same guys that are doing this reordering are the ones that are doing the queue management in the router we have in this network. Well, I mean, they're the same school of guys that decide that putting the short packet first makes the whole life better, including inside the single connection. That's like.
Right. So, Richard Schaffnecker, I just wanted to make a comment that you're focusing very much on rack, but even with packet counting, when you have reordering robustness, which is a when you dynamically adjust to what you're seeing, what you're observing in the network, that's basically almost as good, right?
Okay, so the reason I suggested doing it on time is that everyone's got a view of time. Everyone knows what time is, so they don't have to look at counters in packets if they're encrypted or anything.
Right, but that's a specific implementation detail, right? An implementer could...
No. What I'm saying is it's shared information. Rather than giving them the information as to what your sequence numbers are, they know that if if the norm is, say, quarter of a round trip time, they know what the minimum round trip times are. They know what
to expect,
minimum
basically.
round trip time is. They know how much time they've got.
So what you're saying is that by virtue of saying a quarter of an hour round trip time, you're also trying to limit the extent on which, as you put it, the brakes are, the throttles are,
Yes.
are released
Yeah.
by the hardware
Yes,
designers.
exactly. So if we, and we had an email discussion on this on the TCPM list. I think it was entitled Vicious Circle or Virtuous Circle or something like that. And it's, how can we make it so that it's clear how much time we're giving them, and not just saying, just take the brakes off.
Okay.
Yeah.
So Gary, first, just on the RTT over 8.4 or whatever, if we get path changes, which are very significant, then we will get significant retransmissions if we don't watch out. So there are trade-offs in this space, and I want to be careful that we somehow just think through this, especially when we've got radio resource management, etc. Also choosing timing intervals that can suddenly become very variable.
Right. So that RTT over 8, the idea was we still use the rack mechanisms for finding out what the reordering window is and adapting to it as it changes and whatever. But this is just for the real problem here is how do you get started? Right? Because at the moment rack starts with 3 dupacks.
It does.
And because that's convenient. And I'm saying,
and also it has
the
good
trouble is,
reordering.
If you've just done, a 10 packet back to back, 3 dupacks can be very close together. Can we make them further apart right from the start so that you're using time? So it's only about the start of rack is the problem here. And I'm not saying that rack in TCP has to do this. I'm just saying that if we put rack in L4S, it will have to do this.
It's actually safer to do the dupacks at the beginning.
It is, yeah.
Yeah, okay.
Because the RTT estimate is pretty poor.
And the RTT may be capacity dependent as well, which you wouldn't know.
Yeah, and also you may be doing TFO, and so the last time you measured the RTT was a few hours ago.
Okay.
Yeah.
Michael Abrahamson. So I would just like to lift this discussion to, if we're relaxing the need to order packets in a 5-tuple flow, this should be done at a strategic level as a long-term objective to get all protocols. And this should be the fundamental change in how the internet and its applications work. I love it if we can do this, because it would help so much for so many mediums, radio or RF, the DOCSIS, whatever. It would help hugely, but it needs to be, it can't be just a trickle of the traffic that we have to treat differently. It needs to be in 10 years, this is like the norm. This is 95+% of the traffic.
Rack has been deployed very fast in the TCPs. So it's been implemented very fast. The deployment, I don't know, but the thing about L4S is it is. I've often called it an incrementally deployable clean slate. It's something that gives you that opportunity to get rid of some of your mistakes from the past from day one,
right?
And clear out the clutter,
Right. But so this is not just like Bob standing here for his pet. If we're doing this, it should be done like this is now the new truth. Anything we do going forward is done like that, and it needs to be agreed by wide audience that this is the way we're going. I can't have just a sliver of the traffic be like this. It needs to be a large portion.
Well, this is what David and Gori have been saying to me, that this needs to be agreed by a wide audience. And my take on that is the people that most need to agree it are the ones that will get more of the pain, which is the transport area. The ones that are getting the benefit from it,
yes,
we can assume that they will agree.
Sure.
They just need to be
No, it would make my job moving packets so much easier. So yeah, I totally agree.
Hi, it's Nicolas Kuhn from CNES. I have 3 small comments, and I try not to forget the 3 of them. First, in comparing dupack versus rack in different networks from our previous slides, we have to consider that we have delayed acknowledgements. So sometimes when we have very short retransmission delays at layer 2, sometimes delay acknowledgement can come up with these, and that may not appear in the dupacks. Second, we are not working at the moment on PEPs for satellite constellations, but that is where we're going to have an issue because Gori mentioned huge daily variations. And in here, when you have changes of routes, we have dozens of milliseconds differences in one way day instantly. So that is when we expect to have issues with RAC, but we don't have results to show yet.
But surely you'll also have the issues with 3Q packs then as well.
Yeah.
Yeah.
I mean, I'm not saying.
I mean, you'll have worse issues.
The worst issue, which is if it's only delay based, sure, because then we can somehow think of layer 2 retransmission windows. And on changing the whole thing from getting wing of layer 2 retransmissions, we have to bear in mind that layer 2 packets are smaller than MSS packets. So basically, we have some radio resource optimization, and we don't resend whole TCP packets over the radio links. So there's also some savings in that respect.
Yeah. Okay. Again, if you can put that on the mailing list, that would be very useful. So, because I'm not taking notes at the moment, or the minutes, I guess.
Okay, thank you.
Yeah, thank you.
Okay, it's about time. So, we consumed 2 hours by 3 presentations. Thanks for very productive discussion. Okay, as I mentioned, tomorrow we will have another TCPM meeting, so please attend. And thanks so much for today. This is the end of the meeting. Thank you.